So the first thing we do before actually getting into the real calculus, which is starting with what limits are, then we move on through the derivative, but of course doing a brief explanation of what really calculus is, where it comes from, what's the motivation for studying calculus. But we're going to get to that when we actually get to those sections. Well, so for this class we start with a brief review of some algebraic aspects that will be used very, very often in our class. Like in this case, in this section, rather an appendix. It's one section from almost the back of the textbook. What we're going to do here is review the interval and set notations, solving inequalities, and absolute values. So these are going to be very, very important throughout the semester. It's important to have this to stay sharp on all of this notation, what it means, because a lot of the results that we obtain in this class are not just numbers. You plug in a value, f of 5 equals 3. Okay, that's the answer. No, in calculus, it's a little bit more than just that, depending on what kind of problem we're solving. Answers are not just numbers. Answers might be graphs. Answers might be sets, intervals, depending on the situation. And so of course you have seen this before, interval notation, set notation, but it's always good to review this. And for example, in this case, make a distinction of what parentheses are versus brackets when we describe a set of numbers. For example, when I have the set 3 to 5. What does that set describe? Anyone? 3 to 5.
Set of numbers between 3 and 5, including the
endpoints 3 and 5, right? But what about for 7? But in this case with parentheses.
A set of numbers between the points 4 and 7, but
not including, right? But what if I change one of these to brackets? Yes.
Not including 4, but
including 7 in this case. So, and in this case, the representations of this set, are all these possible ones. So we may have sets that are open on the endpoints, closed on the endpoints. And in these two situations, open and close on one of the endpoints. And in this case here is where we introduce the infinite symbol. For example, this set from 3 to infinity. So what is this set describing, by the way? Yes.
That the answer set is from 3 to positive infinity.
So every single number that is greater than or equal to 3, right? So 3, 4, 5, all the way to infinity. In this case, including infinity. Okay, so I would like to point out a very, very common mistake here. Be careful with the infinity symbol. The infinity symbol never has the bracket. And the reason for this is because, infinity, it's not a number. It's not like I can count 1, 2, 3, 5. Oh, infinity, I'm done. That's like the upper bound. That's a closed interval. It's not. It is in infinity. Ultimately, it's just an idea of something that never ends. And for that reason, that endpoint it remains open. Something that keeps growing and getting bigger and bigger and bigger. All right. So that's what happens with infinity. And of course, we can have 3 to the infinity, 3 to infinity as well. But in this case, the lower bound to be open, that is without including the number 3, in the same way that you guys mentioned before. And so that's the interval notation. That's the set notation, the set builder notation, which has these curly braces. And the way we read this is Well, let me put a numerical example. X, the number, okay, the interval 3 to 5. So for the interval 3 to 5, which in set notation would be x such that x is greater than 3 and less than 5. So the way we read this is, let me use a different color for this. X such that x is greater than 3, oops, and less than 5. All right, this little bar right here, this little bar means such that. So we're describing this interval of numbers between 3 and 5. So it's all the values of x such that are greater than 3 without including the 3 in this case, and less than 5 but without including the 5 in this case. So in this case I chose an open interval as an example, but of course, I mean, we can always choose many examples. Now this stylized R right here, well, actually this can be rewritten the following way: x such that x, this little e that you may have seen before, maybe not. That's another way to describe this set of numbers. Well, this little e right here, it looks like epsilon from the Greek alphabet, but it's not epsilon. This means belongs to. This fancy symbol means belongs to. And well, the way we read this set right here is x such that x belongs to the set of real numbers. So this little r in fancy notation means a set, in the same way that q, with a stylish in this stylish way, means all the rational numbers, and the natural numbers. C for the complex numbers. It's the set of all numbers. It's not a variable, right? It's just a symbol to describe a particular set in this case. All right. So I mean, again, this is just a brief review about these ways to represent intervals. How do they look like? Very important when it comes to how they look like in graphs. For example, let's say a equals to 3 and 5. This is describing this set 3 and 5 with parentheses in this case. So the main point here is, when it comes to describing this as graphs, there's only one main difference, and that one main difference is that whenever we have open sets, or that is parentheses, in the graph they are reflected in the form of open bubbles, open circle. That means those holes that you can get close and close to that value, but not hitting that value, because otherwise what happens? You get swallowed by that hole. That's a typical idea that we explain that we just need to explain why we are not choosing, why do we exclude that value. However, on the other hand, okay, whenever we have closed set, I mean a set for which the endpoints are closed, we include those values, we distinguish them in their graph notation by having filled in bubbles. So are there any questions about this? Hopefully all this rings a bell from basic algebra, pre-calculus, college algebra, or any other class. Again, we're going to be using this notation very often when we talk about limits, continuity, and many different topics. Inequalities, so that's another aspect that we need to be sharp on, because again, when we describe, for example, when we analyze functions, you know how graphs of function on some intervals go up, that means increase, then decrease, or remain constant. So we will describe those intervals or those values of x as sets in the form of inequality. So, and in some cases we may need to solve certain inequalities. So let's have a look at some of the rules. Well, this first rule or definition or property, if you will, means, well, if we have this inequality a less than b, all right, what we can do is add a number, add or subtract any number, but the key aspect here is that the inequality, the symbol of the inequality or the direction of the inequality remains the same, right? You can add and subtract, and that doesn't change the inequality symbol. However, for the second inequality tells us that we can combine two inequalities together. You know, when you have like 3 less than 5 and 4 less than 7, you can add them together. 3 plus 4, 5 plus 7. 3 plus 4 is 7. 5 plus 7 is that a 12, and the inequality, it's still a logical sentence, right? Because 5 is still less than 12. So that's what this second property is telling us here. All right. We need to be very careful with number 3 and 4. So for 3 and 4, properties 3 and 4 are about multiplying both sides of the inequality by a number. And in this case, we divided it into two cases. The first case for number 3 is when we multiply both sides of the inequality by a constant c, whatever that number is, but notice c is greater than 0. That means when we multiply an inequality by a positive number, that doesn't change the direction of the inequality. For example, when I have 3 less than 5, if I multiply both sides by 2, 2 times 3 is 6, 5 times 2 is 10. Is the direction of the inequality still the same? Is 6 still less than 10? So that's what this third property is telling us. However, number 4 tells us the following. For example, okay, let me take the same example, 3 and 5. But in this case, if I multiply by a negative number, let's say by negative 3. Okay, what do we get here? Negative 3 times 3, that's a negative 9. What is this? 5 times negative 3, that's a negative 15. But it's still, is this still a logical sentence? Is it true that negative 9 is less than negative 15? No, so that's why we always reverse the inequality symbol to keep the integrity of a logical sentence. In this case, well, to denote that negative 9 is greater than negative 15. All right. And a very similar for number 5 is whenever we have, okay, again, 3 less than 5. So when we have 3 less than 5, we can reverse or find the reciprocals. But in this case, is 1/3 less than 1/5? I don't think so. So that's why we need to reverse this. All right, we need to reverse that. And well, so these are like pretty basic properties of inequalities. I mean, it's nothing new. It's something you've seen before, maybe more than once. but it's worth to have a second look at it as a refresh, because again we're gonna make use of this very often. So how about we solve some inequalities? So we still have some time to go about a couple of examples. So, well, the first example, let's solve this inequality. So we have 1 plus x less than 7x plus 5. All right. Well, the way we solve inequalities is in a very similar way that we solve equation. Whatever you do on one side, you do it on the other side. It's the same thing. The only difference is that when we multiply or divide by a negative numbers, that's what changes the whole game and need to reverse the inequality symbol. So that's all we do. But other than that, it's pretty much the same. So let's go ahead and solve this inequality. So just like in equations, we want to have all the variable terms on the left hand side of the inequality and all the constant terms on the right hand side of the inequality. And in fact, it's better to do it this way when it comes to inequalities. I'll show you why. Well, in this case, I have this 7x, and I'm going to move the 7x to the left hand side of the inequality by doing the inverse operation, because of course this 7x right here implies a plus, so we need to do the opposite in sign. Cancel. X minus 7x, that's negative 6x, and that's less than 5. And then from here, well, let's subtract 1 from both sides to get negative 6x, rather less than 4. Okay? And we are only one step away to get this inequality solved. And to get x by itself, multiply, or rather divide both sides by negative 6. But be careful. What happens when we multiply or divide by a negative number?
Flip the sign.
Flip the inequality sign, right? So that's x. 4 over 6, which reduces to 2/3. Actually negative, but be sure to reverse the inequality sign. All right. For letter B, we have this kind of inequality that you may have seen before. It's an inequality that, as opposed to like letters A and C, this inequality right here has 3 sides and not just 2 sides like A and B. You want to ask something?
We write the solution range, like the solution range minus 2 by 3.
Yes, it's some kind of expressing the function of a shifted the range of a shifted function, or the domain of a shifted function. Yeah, that's something that yes, we will use this piece of information when we look at the translations of functions. So, well, whenever we have something like this, well, we have a 3x minus 2 bounded between 4 inclusive and 13 exclusive, and in this case we include the lower endpoint, but we don't include the upper endpoint. So, well, to solve this kind of inequalities, our main goal is to leave the variable x, the letter x, by itself in the center. So we need to do a couple of operations, nothing too crazy, like adding 2 in this case. On the 3 sides of the inequality, it's not like on both sides like we did before. In this case, it's on the 3 sides. Well, 4 plus 2 equals to 6, less than or equal 3x. Oops. Less than 13 plus 3, that's a 16. And we're only one step away to get the x by itself. Well, so all we have to do is divide the 3 sides by 3. That's going to give us 6 over 3, which is 2, and 3 over 3, which is 1. That's the x that we want. Yes?
I think it's supposed to be plus 2.
Plus 2? Well, that's what I meant, but not what I wrote. Thank you. Yep. So that's over 16, that's 15. Yes, 15. Thank you. So 15 over, okay, yeah, let's do the 3. Oh, much better. So that's 2 and 5. All right. Now, this last inequality, of course, we can interpret it in different ways. So number one, we can, okay, let me box this final answer. So another way to express this answer is between 2 and 5, brackets for 2, parentheses for 5. So that's using interval notation. Using set notation, x such that just copy this inequality. Alright, and of course we can draw the graph of this, but in this case be careful because for 2 is a solid bubble and an open bubble for 5. Oops. Alright, if this is 0 right here, this is 2, this is 5, and we can highlight, usually we highlight this set, right? But just making sure that you have a solid bubble for the endpoint that corresponds to the bracket and an open bubble for the endpoint that corresponds to the parentheses. Alright? Of course, we can do the same for the previous one from negative 2/3. But in this case, this one should be, oops. This is 0 right here, and in this case, these all go on forever to positive infinity, right? That's how we describe that inequality, that solution to that inequality using a graph. Or in the interval notation as well, parentheses, negative 2/3, all the way to infinity. All right?